Good morning. My name is Tim Canter, and I'm here to talk about the pull plug sedimentation basin for medium and small scale flushed areas. Before we get going, we need to thank USDA NEFA for funding the project, or at least part of the project, through the management of nutrients for reuse or manure, a larger grant that we're working on. Also like to thank Tang and Joe from the University of Missouri, Rick Stowell from the University of Nebraska, and Troy Chalkley from the USDA NRCS. So always good form to talk about what you're going to talk about before you talk about it. The PPSB introduction is going to kick us off, and we're going to get into the size, what this thing is, how it operates, etc. And that's going to fold right into the performance and what we've seen within or among various operations of the system. Get into some insight into what other people are saying for similar systems or what can be expected there, and then next steps and future research to wrap things up. So the PPSB is essentially a sedimentation basin. It is a liquid solids separation device. It's a sedimentation basin with a bit of a twist on it, and it can probably best be related to a weeping wall in terms of both cost, I think, as well as performance. This is relatively a new development, a new technology. There's only about 6 installations in Missouri, and the USDA has claimed that among those 6 installations, they're seeing about a 90% solids retention, which I think is approximately where weeping walls are. We got involved earlier this year, maybe 6-8 months ago. We haven't been working on it too terribly long. These installations have been designed, I wouldn't call it trial and error, but this seems to work sort of process. And so we wanted to collect some empirical data, begin to put that together so that these could be scaled smaller or larger in the future. These have been applied to dairies or flush dairies with herd sizes between 120 to 160, maybe as high as 180, but a pretty tight herd size. And there's quite a few of those, I think, around the state of Missouri and probably throughout the country. We've got 2 data points on the cost of this. One, the 26,000 was a pre-construction estimate from USDA, and that seems a little bit low. We've gotten another from a producer, a farmer, that said it was $60,000 for him to build the PPSB and adjoining sand lane. So he was unable to split those out, I think, from these, and we'll go along and continue to collect data points on cost. But I think that it can probably be expected to be somewhere between $35,000 and $45,000 for the PPSB alone. Now, that figure, that number is surely going to change and will probably be variable depending upon location in the country, the topography of the surrounding area, as well as the geology of the land involved and what has to be done in order to actually install this, of course. The dimensions of the PPSB have been relatively consistent for these 120 to 160 head. The most important design parameter, we believe, is the depth. The curb to floor height of 6 feet has been chosen and has been applied, I think, to all. It's a 1 foot to 1.5 foot of freeboard, so a minimum operating depth of 4.5 feet, I think ideally 5 feet. And the reason that's needed is to allow solids to both settle as well as to provide some ability for the mat to form. The idea is that there's a floating mat that forms on top from undigested fiber or fiber bedding, and then water is then filtered through that mat as it forms, very similar to the weeping wall. Now, the 20 by 20 length and width of the flat floor as seen below is strictly a solid storage, solids capacity thing. They target having to clean this thing out every 3 to 4 months, but it varies greatly depending on rations and the type of bedding used. The ramp that leads down to that flat floor is based on that 6 foot and applying a 12 to 1 slope to it. I know it says 5 degrees here, it's really like 4.76, but the 12 to 1 was seen as the maximum slope possible to minimize costs while also allowing for a skid steer loader to get down there and safely remove bedding from down below. The quote unquote pull plug, which is really this twist on the sedimentation basin, it has been a 6-inch diameter, typically PVC pipe that fits into a slip joint at the bottom of the basin. That is pulled when the basin becomes full. The basin is full when the settled solids on the bottom meet the layer of floating solids on the top, and that interface is formed, at which point that plug is pulled, allowing any additional water to drain from the basin. That whole plug is surrounded by a 12-inch diameter pipe, perforated, that acts as a baffle to allow that mat to form versus being flushed down the drain. That pipe, that baffle, extends up to the curb height and then drops anywhere from 1.5 to 2 feet below the operational water surface. This can be arranged on the back of a flush barn, a freestall barn, in a couple different ways. It can be parallel to water flow and you just funnel the flow in. However, more than likely, just the way things work out and for cost of construction, it's normally done perpendicular to the flow. And so this is just one example on the right where the water would flow down, hit a curb. Perhaps a sand lane is integrated into that flow as it flows from right to left, and then it does a hairpin turn and then flows into that basin. The layout's really going to be dependent upon what's there on site already and what makes this most cost effective. Here's a picture of it in operation. You can see the mat formed. This is a very choppy mat. This is one with high hydraulic loading. We'll talk about in a bit. The water from the freestall flows out of the barn, makes a left turn 90 degrees, and then flows into the basin. The flush water from the parlor, milking parlor, and holding pen come down the side of the barn, and it enters the basin near the ramp, basically under the red rail on the left picture. Any water that's to go through this really needs to enter ideally through the ramp or across the ramp or as near to that point as possible to prevent turbulence, which would have a negative effect on mat formation. This is a view of a second installation we'll talk about, a much less hydraulic load. You can see there's not quite the undulations and cracks in the mat above. Pull plug up on the left in the picture on the left, and then the picture on the right is a view of that pull plug during cleaning. There's a great deal of distance between the PPSB at this installation and the receiving lagoon, so the operators opt not to pull the plug for fear of having that line clogged. And they don't seem to have a problem with that in terms of unloading the solids. These pictures here are of that pull plug in operation. The one on the left is between flushes, so you always get a little bit of a trickle of water. You can see the line on the baffle where the hydraulic jump occurs during the flush, and the right is a picture of that same pull plug during flush. So we took a look at two dairies, a little bit different, kind of similar in size. The BR dairy and FM dairy, the names have been changed to protect the guilty here. BR is a sand-bedded dairy. Their setup is one where they've got 4 flush lanes, 2 on the right side of the barn, 2 on the left. They flush 7,000 gallons down the right side, so 3,500 gallons per lane. They have one tower. It takes them about an hour to recharge that tower before they can then flush the left side of their barn. That means that the PPSB is seeing about 7,000 gallons each flush, because by the time that hour passes, the water is evacuated, the PPSB by and large, and they do their flush 2 times a day, morning and night. FDM dairy is mattress bedding with cedar shavings, similar herd size. Also, the barn is similar in design. They have 4 lanes, but they have 4 valves, and they've got 2 towers. So they just walk down the line and they'll hit valve after valve after valve in sequence. So they end up sending about 28,000 gallons over the course of maybe 10 minutes, perhaps less. So that hydraulic load is much greater. As you saw in the pictures before, the first pictures with the undulating, very rough looking mat, that's the one with the hydraulic loading that's higher. They flush 3 times a day. So higher concentration of solids in the morning and presumably approximately half the load in the afternoon and the evening. So our first step in looking at this is hydraulic loading. We've been working on this now for about 6 months, so kind of in the infancy, particularly with COVID, not being able to do a lot of travel, that sort of thing. But BR dairy, that 7,000 gallons applied to the operational liquid level, so the surface area at about 4.5 to 5 feet in depth. This is calculated, I think, at 4.5 feet. That ends up being 4.7 gallons per square foot. The linear hydraulic loading, 350 gallons, that's across the maintenance ramp, so 20 feet wide. And then the weir loading rate is on that 6-inch pipe, 3.5 clean outs per year. So they are cleaning out every 3 to 4 months. We just split the difference there and calculate the number of clean outs per year. F to M dairy, much higher load. That's, excuse me, I misspoke before. Both of these are, I think, are on a 5-foot operational water level. The F to M dairy, the dimensions are not much different than BR. BR dairy is the 20 by 20 flat floor that we saw before. FM dairy is maybe 3 feet wider, 4 feet longer, but very, very close in size. So the hydraulic loading is much higher because they're flushing essentially 4 times the amount of water through it. And with the cedar shavings, they're running 10 cleanouts per year every 5 weeks. Probably not terribly ideal, but that's what it is. So we tested these different things for these different dairies in the match for nitrogen, phosphorus, and potassium. The actual weight of the phosphorus in the P2O5 is about 44% of what we see here, and that's reflected in the numbers there. So that's the actual weight of the phosphorus. What we see at the sand dairy, the BR dairy, is stratification. You get 2 feet on top and 4 feet on the bottom. The 2 feet on top is undigested fiber. The 4 feet on bottom is undigested grain and a lot of kind of sandy loomy. Their sand lane's about 60, 70% effective. So we sampled from both, and note this is 6 feet all the way up to the curb. Their lower hydraulic load means that they can allow this thing to begin to breach the top of that curb before they have to clean it out. F to M dairy is a little bit different. The high hydraulic load means they have to clean it out when those bottom top interfaces meet. And it is still about 1 foot to 1.5 feet below that curb height because of the hydraulic jump associated with that hydraulic load. Now, it is all fiber throughout that PPSB for FM, but we did notice a difference between what appeared to be older fiber and newer fiber. Older fiber maybe closer to the top or closer to the back by the pull plug. Newer fiber, maybe lower, but definitely more towards the maintenance ramp. And we did see a significant difference in nutrients in those. Interesting thing is the nitrogen concentration between the two dairies and the old fiber for FM and the top layer at BR, scary close. No, we needed to consider nutrient production to figure out how many nutrients were being retained. So we referenced Ppsb for production, and then to account for the cedar chips, we talked to the supplier of the cedar chips, got the volume being supplied per annum as well as the weight, and then referenced some Canadian research for the nutrient concentration in stem wood of conifers. So using that, we're able to produce or generate the annual production for the BR dairy and got percent retention as reported here per annum. FM dairy, the contribution from the wood chips negligible. But this was a significant difference in terms of retention, and we ask ourselves why. We turn to literature and see what they had to say, and there's not a lot in terms of liquid solid separation, sort of pre-treatment screening for nutrient retention. There was one paper talked about mechanical screens, 1.5 millimeter pore size. Very little nutrient retention can be expected based on the size of particle being retained. And we looked at a 2-stage weeping wall. They reported a little bit higher nutrient retention, and it makes sense. Although the mechanical screen is producing a very consistent quality of water and very consistent quality of solids, the weeping wall, presumably the PPSB, start out with capturing coarser solids. And then over time, as they begin to fill up, the nominal pore size, equivalent nominal pore size decreases, and you are capturing a smaller and smaller particle. And so it makes sense why they would have greater nitrogen and phosphorus retention. TKN being ammonia plus organic nitrogen, does not include nitrate, nitrite, but that's probably negligible anyway. We compare that to the PPSB and the sand bed PPSB, not the same, but it's in the ballpark. But again, that cedar chip PPSB much, much higher. And again, why? So our best guess at that why is that the cedar chips, particularly fresh, not recycled cedar chips, are providing absorption and adsorption to this. Adsorption being that organic particles are sticking to larger organic particles, similar to activated carbon, although not as effective using the cedar chips, but it's still occurring. The absorption coming from a bit of a discussion with the cedar chip provider, them saying that these are extraordinarily dry chips and we need to investigate the moisture content, but they would tend to, being dry, absorb more fluid than or moisture than a something that had a higher moisture content going in, and perhaps smaller particles, dissolved particles, are being absorbed into that wood matrix along with the moisture. So that's something to look at as well, and will become part of our next steps. So what we need to do is definitely look at the create a composite of the nutrient concentrations within that PPSB at FM Dairy. We assumed a 50-50 split on the new versus the old fiber. It's probably not right. It was just a visual observation. So sample more locations, figure out what that is. Evaluate the effects of solids and hydraulic loading. What happens if we spread that flush out so it's not seeing that 28,000 gallons? What's the effect? Better or worse? As and solids loading as well. What happens if we only flush twice a day versus thrice a day? Does that have a positive or negative effect? Develop the system mass balance by trying to get a better handle of what the cows are actually producing versus using Ppsb as a reference. Also looking at the lagoon, finding out what's going on there and presenting a whole system mass balance. Explore that adsorption and absorption a little bit more thoroughly, and look at the temporal changes because of that nutrient concentration difference between the old and the new fiber. Why is that occurring, and why is there a difference? I believe there's a Q&A on the back of this live, but if you need to get in touch with me, email is the best way to do so. And I look forward to taking questions and hopefully hearing from you in the future.